So we know how the decision tree classifier and decision tree regressor works. Now it is time to look into ensemble models. So what's an ensemble model? First we need to understand that. There is a hard voting classifier and there is a soft voting classifier, two kinds of ensemble models. Basically, ensemble model means you build a logistic regression model, an SVM model, and a decision tree. You pass your record to all three models and make it predict based on majority voting. If you try to make the ultimate prediction, right? That's called as hard voting classifier. So instead of using one model's prediction, we are using multiple models predictions. So to train this, we'll use the same data. Okay, and then we pass a new record or the test record into three models, and we'll get the predictions. We take the majority voting, right? This is like our current voting, current election democracy voting thing. Here out of three, two actually predicted 0. So ultimate ensemble models prediction is going to be 0. So do we have class to do this? Yes, we have. We have voting classifier, a class called as voting classifier, which takes multiple voting classifiers, estimators, and then you can specify whether it is hard or soft. Right? We have seen hard voting classifier. This is majority voting is the hard voting classifier. Soft voting classifier. In soft voting classifier, each model's probability it will take, right? One class probability. Okay, and then it will try to average all of it. So in the first model, 49%, right? It predicted 0. In the second model, 99%, it predicted 1. In the third model, also 49%, it predicted 0. By edge of 0.01, it failed to become 1. Right? But if you take average, right, it becomes 0.66. On an average, this is greater than 0.5. So you can predict this record belongs to 1 rather than 0. This is soft voting classifier. Soft voting classifier is better compared to hard voting classifier because it looks into the strongest prediction, and then tries to make the decision. Got it? The probability is the major thing we consider in soft voting classifier. Okay.
Sir, you are taking 0 and 1. Is it a classification problem?
Yeah, it's a classification problem.
Okay.
In regression, right, it is always average. You take multiple models, make them predict. All the predictions average you take, and that you predict as the ultimate prediction.
Okay.
So you understood the difference between hard voting and soft voting classifier, right? How it works.
Yes, sir.
Very simple. Yeah. So I have taken the data set, splitted it, and then I took random forest classifier, but we'll understand what it is in a moment. Voting classifier is the class which actually takes all the other classifiers, estimators. Right? I instantiated all three algorithms, and then voting classifier is taking the algorithms in a list of tuples. Okay, estimators is a list of tuples, and then voting is hard, but I fitted the model. Right now I am predicting. So here I am predicting individual models here. So CLF in the list of models, right? Individual models also I trained here. Somewhere. No, here itself I trained. Yeah, here I trained. Individual model I am training, and then using individual model I am predicting, and I am calculating the scores of individual models, and voting classifier also I am predicting here. Right? I trained voting classifier here, individual classifiers here. I am looking at the predictive power of individual classifiers and the voting classifier. If you see logistic regression, 86.4, 89.6, 89.6, but hard voting classifier gave a little more accuracy than the individual classifiers. Right, that's the power of ensemble model. Ensemble model will work a little better than the individual algorithms. So to do soft voting classifier, you specify voting is equal to soft. That's it. Okay, and then you look at the soft voting classifier. It is even better than the hard voting classifier. It is 91.2. Here it is 92. Right. So voting classifier, you can ensemble model. This is called as heterogeneous ensemble model. Here we are using 3 different algorithms to build an ensemble model that is called as heterogeneous ensemble model. In heterogeneous, there is soft voting and hard voting classifier. You can say hard, so homogeneous when you take the same algorithm multiple times. You take same algorithm multiple times and try to build this model. But generally, if you take same algorithm, right, it may not give you decision trees will give you same algorithm multiple times with different subsets of data. Okay, we'll see that in a moment. That is random forest or the bagging classifier. Okay,
So, one
so
second, sir.
any questions? Yeah.
Yes, hard. Sorry. So hard voting classifier is actually takes the maximum of the prediction, right, from one of the 3.
Yeah, majority voting we call it as majority voting.
Is it soft or hard?
Hard.
Hard is the majority.
Probabilities, average of probabilities is soft.
Soft. Okay. In hard, voting classifier, what is the accuracy we got?
91.2.
So how did it take it? Is it taking only one of these or
No, like this one. Majority voting it will take. 3 models we built. Out of all 3, which one, which class is more? That class it will take.
But it looks like it has not taken any of the 3, right? It is calculating something.
How did you know it didn't took any of those?
No, it should take actually one of these, right?
No, are you looking at this code block and trying to talk?
No, the accuracy of logistic regression, random forest, and SEC. And
Yeah, individual models I tried to make predictions and show the difference there. How the hard voting classifier is working and individual models working. Yeah, go ahead now. I didn't get your question.
Yeah. So the hard voting classifier is actually takes the accuracy of one of these 3, or it actually trains itself separately.
Majority voting. Majority voting in the sense, if logistic regression and SVM are saying 1 and random forest is saying 0, it will take 1 as the prediction. If all 3 says 1, it will take 1. All 3 says 0, it will take 0. 2 says 0, 1 says 1, then it takes 0, like that.
Okay. So in soft, let's say this is for a soft voting classifier. So it takes the average of all the 3, right?
Probabilities.
But what it takes here in hard voting classifier. So how we got this 912, 0.912?
See, each model is predicting, right?
Yeah.
Each individual model is predicting, right?
Yes.
And the voting classifier will look at right. Maybe I'll try to answer it in different way.
Yeah.
So maybe right out of all the 100 records, 86 records are being predicted as 1 in all 3 classes. Okay. And some records are predicted as 1 in 18. Random forest and SVM. Maybe around 4% records predicted as 1 in the random forest and SVM. So it took the majority voting here. That's where it actually became like Most of the times, right? It is like this. We three are predicting. Maybe you, me, and Giri are predicting. That I may say 86% of the times once. Right? You both may say, maybe 87% of the times one. Right? Same thing. Whatever I said, what you say is also we should match. Right? We three should. Majority should actually vote. It is like elections only. Right? If I choose a person, I may choose one person, but if many people choose, the person will change, right? Like that it is. Did I answer your question or?
No, just simply I take like, this is instead of hard, it is a soft. There we are calculating the average, but in hard, how this 9.0.912 is, coming out?
This is the diagram. I don't know why you are unable to understand. This is the diagram, right? This
Okay.
diagram, did you understood?
Sir, here thing is like as for hardcore,
Ah.
0 or 1, sir. So
Ah.
it needs to be display either 0 or 1.
No, this is accuracy score. This is not probability.
So accuracy score means now we are using 3 models here.
Ah.
In the out of 3 models, like which accuracy hard voting is taking? That's the
That's what I'm saying. It will actually for each record it will have only one outcome, either one or zero. That decision is made by looking at the majority voting. After that one or zero is there, the accuracy is calculated.
okay.
Got it, Sisram garu?
They're just trying to understand it.
Sir, if you don't mind, can I just
Please, sir.
elaborate,
Please, I
sir?
am unable to explain. Please.
Yeah. Yeah. So I'll just try to elaborate. I may be wrong, but just
Yeah.
give me a minute to explain.
Yeah, please.
Assume that there are 4 records, the input records. I pass it on and I already build a model. So for 4 records, first record logistic regression gave assume that it's a hard voting. Logistic regression gave a number, and similarly random forest also gave some number and SVC. So finally, what one is whatever logistic regression and random forest, whatever they predicted, because it's by majority, that one. So hard voting classifier finally said, yeah, a predicted value equal to 1. Okay, just assume this is the case. Similarly, for second record also, second record random forest classifier and SVC gave, let's say, 0 because that's a majority. So final decision for the hard voting is 0. So that's the one. Similarly for third and fourth. So in this way, predictions happened. So now you can imagine out of 4 records, the number of times logistic regression can predict will be probably less than what are the number of times hard voting can predict correctly. At least, do you agree with that, Shishram garu?
Yes.
Yeah, so that's exactly what is happening here. So maybe you are thinking that, hey, boss, here the accuracy score of all these 3 are some 8.9. Suddenly, how come hard voting can be 0.91? So the reason is because hard voting finally takes one of these best ones. So that's where obviously its accuracy score is going to be more. Accuracy score.
Is that the way you are thinking? Like, all these three models are predicting 86, 89, and 89. How come we get 92, right? That's what you're thinking?
No, I'm not saying it shouldn't get, but how it is getting.
See, it is, no, sometimes logistics regression may say 1. For some records, logistic regression, random forest may say 1. For some records, random forest and SVM say 1. For some records, logistic regression and SVC may say 1, right? That way, the number of ones may increase. That way, the number of ones may increase or decrease, or zeros may increase, zeros may decrease, but the accuracy matches.
Yes.
Right? Instead of taking one opinion, we are taking 3 opinions and trying to conclude.
Yes, sir. Got it now.
All right. So it's a simple thing, maybe, And in this in this, instead of taking 0, 1, we are taking probability and taking average on the soft voting classifier. Okay, maybe look at the notes once, maybe you'll get more clarity.
Yeah, those three algorithms we have taken, right? Is that those three, or we can take more, or
anything you can take. Voting classifier will take any predictor here.
Okay.
Any predictor, any number of predictors it will take. This is magnified as bagging, pasting, random forest, or whatever, right? Boosting, all those ensemble models. These are all called as ensemble models. Okay. So now we look at bagging and pasting. These are two ensemble techniques which are homogeneous ensemble models. So in bagging or pasting.
I have one question, sir.
Yeah, please.
Because we are taking multiple algorithms and then finally arriving at something, so the runtime is going to be higher.
Yeah, it will take more time.
Okay.
In training and prediction also it will take, but prediction always is going to be like, in a loop you are going to predict and try to submit, or maybe in a batch you are going to do it. So we can control the prediction time, we can control, but training time we cannot. It will take time, more time.
Yeah, sure.
At that point, we should understand, right? Training takes more time, prediction takes less time. Many people doesn't know. Many people in the industry doesn't know this simple thing because they never concentrate. I think they never know. They do models, they build things, but they never concentrate on how exactly it works. So in bagging and pasting, right, we are moving on to the new ensemble models. Bagging and pasting estimate models are use same algorithms, right? It uses decision tree algorithms, but train them on different random subsets of the training set. Let me try to show one diagram here. Let me see. Yeah, this is here. So I will say, right, in decision trees, we have seen that individual decision trees will overfit. But when you build a bagging and pasting or random fast algorithm, they will not overfit. The overfitting problem will get resolved. Okay, I'll show how with a simple example. But first, let us see how the bagging and pasting algorithms work. Bagging, when sampling is performed without replacement, we can call it as bagging. Sampling is performed, with replacement, without replacement, then it is called as pasting. So here, what is with replacement and without replacement? This is bagging algorithm. This is bagging. Okay. So suppose that there are 4 records in your train set. Okay. And the bagging algorithm will do bootstrapping. In resampling techniques, we have seen bootstrapping, right? 37% of the data will be taken aside and 67% will take and reproduce 100 records. With 60%, 67% data, we will produce 100% data by replacing, sample with replacement. Okay, sampling with replacement, we call it as, right? So I have taken 1, 2, 3 records, and 3 is copy pasted to produce 4 records. This is called as bootstrapping. Right? On this, we will build a tree algorithm. Okay. Again, I have taken 1, 2, 4. 4 was replaced, right? Copy pasted, right? Not replaced, copy pasted. And then we are building a tree algorithm. And again, we take 1, 2, 4, and 1 is replaced. So we are building three different decision tree models and trying to make hard voting classification on that. That is called as bagging. Okay. Got it? Any questions? Bagging classifier, this is called. Any questions?
How much percentage to be replaced? Is it configurable, sir, generally?
Yeah.
Generally,
yeah. So let us look at that. Sampling with replacement. N estimators is the hyperparameter to choose whether 3 or 2 or 100 or 200, right? 200 models you want to build, okay? And then max samples, right? The number of samples to draw from X to train each base estimator, right? If you specify, right, 3, it will take 3 and copy paste 1. If you take 2 only, it will take 2 and then copy paste those 2 and produce 4, like that it is. Okay. And one more thing is max samples, max features, features also. You can choose, number of columns also. How many columns you want to choose, right? For each of this tree, how many rows, how many columns? Here we have only x1, x2. If you have xn, I may choose 4 features here, 4 features here, 4 features here, like that. So we do subsampling of data and then build. Bootstrap. By default, it is true. If it is false, right, it becomes pasting. In pasting, what will happen? It will actually take the subsample only. It will not it will not copy paste. Tree building and model prediction is all same. Got it? In the bagging classifier, there is a attribute called as a bootstrap. If you say false, it becomes pasting. If you say true, it becomes bagging. If you say false, it becomes pasting. Got it? Got it?
Yes, sir. Question. Can you please go to that slide, sir? Yeah. So here the building the tree is again our ensemble model, sir.
Yeah.
Okay. So it's one more layer coming in. So it's something like that to make it more.
Sampling is the layer coming in. That's it.
Okay.
In our normal, ensemble models, we did not do sampling. We took the data and then built models, 3 models, and then we are trying to use that as the ultimate model to make predictions. Majority voting as the ultimate model. In the bagging pasting, there is a sampling technique, right? On the subsamples, so sampling is done on rows and columns both. And do we want to do bootstrapping on rows and columns? That's the feature. Bootstrap, this is for rows. Bootstrap features, this is for columns. We can bootstrap columns also. We can copy paste columns also. Got it?
Yeah, got it, sir. So because with the multiple samples, the same ensemble model is coming. That is why it's becoming finally homogeneous. Is that so, sir?
No,
Finally,
these are all same algorithm, right? Then that's where we call it as homogeneous.
Yeah. When you say same, it's an ensemble, right?
No, decision tree models. Right? The algorithm we choose is what makes a homogeneous or heterogeneous. These are all decision trees, right? These are all decision trees. But here, one is logistic regression, another is random forest, another is SVM. That is heterogeneous.
Oh, okay. Okay.
Got it? In the ensemble model, all the models are built using same algorithm, then you call it as homogeneous.
Okay.
If they are different, then you call it as heterogeneous.
Okay, sir.
So these are the these are kind of miniature versions of deep learning. Deep learning, initially the researchers actually started with ensemble models, and then they actually made deep learning algorithms. So
yeah, sir.
Yeah.
In bootstrapping, we say like we take the number of rows from the train set, right? And in this example, we are taking 3 and producing 1. So how is that 1 produced? Is it a percentage of the 3, or how many we can produce?
Where you are talking in the sampling?
Bagging sampling. So from the train set, there are 4 records. We are taking 3 each time, and we are adding 1.
We are copy pasting.
Yeah, taking 3 is actually mentioned, right? Min samples or max samples. But how that 1 is produced? Is it the percentage of the 3?
Random. It is random. There is no control over it.
Random.
Randomly, it will pick a record and then copy paste it.
Only 1 record?
Here 1 record, because we are trying to produce the size of the train set. If it is 100 records, right, it will try to produce 100. it will take 67 records and try to copy 33 records from the 67 and paste it and produce 100 records.
So in this case, if we say to sample size equal to 2, it produces the 50% extra, right?
Yeah, yeah.
It has actually taken 2, it produces 2 more to make it as a train set. Okay.
Yeah, yeah. Right, got it? Ultimately, bootstrapping resampling technique is what is used here.
Mm-hmm.
We have seen resampling techniques, right? Bootstrapping resampling.
Yes.
Same thing is used here. Yeah, the term also I used the same thing, right? Bootstrap, because even if I don't explain, you look at the API, you will understand what is bootstrapping. You know it. Okay.
Yes.
So n jobs is the number of parallel processes it need to use, right? In our computer, there may be multiple processors. How many processors it should be using, right? Random state, verbose, n jobs, warm state. I don't know what this is. When set to reuse the solution of the previous call to fit and add more estimators. Okay. Okay. So it will actually use the previous iterations, tree and try to improvise in the warm state, warm start, if you say, right? Every iteration, it will actually try to use the previous one and then try to produce it, produce the new one, rather than creating a new tree altogether, or new tree estimators, more estimators to the Ensemble model. So OOB score, I'll explain in a moment. You got clarity, right? What is bagging and what is pasting? So here, right, these are all parallel models. You can actually train each model on different computer and then combine, keep the models on different computer. You take the record, pass to different computers, make them predict, collect the results, and take an ultimate decision also. You can actually manually build it. If you are not using the bagging classifier provided by scikit-learn, right, you can manually build it. So the Spark is the language which actually does the parallel processing, and it works on huge data sets. It does that. It actually keeps the data in different servers and then parallelly processes these and gets the results onto one server and returns it back. Okay, that is parallel processing. So these are parallel. Okay? And in deep learning, there will be parallel and sequential both. Sequential means if you have one more layer of models, one more layer of models, one more layer of models, that's called a sequential. These outcomes will be used by those. Those outcomes will be used by those, like that. We'll talk about that later, but don't be worried. But bagging and pasting you understood here, and how to build a bagging model. I'll explain what is OOB score in a moment. And bagging classifier I have taken, and then decision tree, right? This is the algorithm on which we are actually building bagging classifier. But by default, the algorithm is going to be decision tree, I think. See, by default, now if you don't specify anything, right? If you just do bagging classifier and n estimators like that, if you say it will take decision trees only, right? You can use logistic regression also here. I have used it here. Bagging classifier with logistic regression. But how many estimators? 500 estimators. Here in the diagram I am showing only 3. But in the algorithm, right, I have taken 500 estimators. Max samples. I have taken 100 records each, right, for each tree to build 100 records. Bootstrap false, I said. This is pasting algorithm. And this is pasting, not the bagging. If you say true, it's going to
So we lost your voice.
Yeah.
Can you hear me? I lost Or here I connected to mobile.
Yeah,
Yes,
we
sir.
are able to hear it.
Yeah. So okay. Says bad network quality. We know. Okay. So here the decision tree classifier at n estimators, max samples, bootstrapping false, n jobs is equal to -1, right? It chooses based on the availability of the resources. It's a by default value, I think, n jobs. Right? The number of jobs to run in parallel, right? -1 means using all processors. Oh my God, all processors. Using all processors, how many, how many models it can build? It should build. Don't put a -1. Sometimes system may get stuck. All process will be taken by the algorithm, so it gets stuck. So random state is like, every time you run the model, it chooses the same 100 records. This is uh, the object creation, right? The bagging class for object we created, and then fitted the model, and then predicted, right? So now we are calculating accuracy. We have got a 0.91 accuracy. Okay, individual decision tree 0.85. Bagging classifier is working better. Okay, in this bagging classifier, right? Sorry, this is pasting. Sorry, in the pasting it is, and bagging, right? Bootstrapping is equal to true. I kept. I got 84% only. So on some data sets, the bootstrapping works. Some data sets not. Especially when the data sets are imbalanced, bootstrapping works best. If the data sets are not imbalanced, right, bootstrapping doesn't add any value to the decision trees. Okay, so why? We have already seen it in the anomaly detection. We were actually using smart and other techniques to create synthetic data, or kind of trying to reproduce the minority record pattern in the data set so that the algorithm will understand, right? The same thing works here when you do bootstrapping, right? When there is the data set is imbalanced, then the model will work best. In this, there is a concept called as out of bag evaluation. So in general, whenever we are building a model, we are doing cross validation, right? Do you know what is? Do you remember what is cross validation score? Do you remember what is cross validation score? How is it useful? Cross validation score, how is it useful?
A relation between columns or anything like.
No, cross validation score is like, you take the data set and split that into n pieces, right? Maybe 10 pieces, and keep, if you say CV is equal to 10, it takes the train set, makes that into 10 pieces, and keeps the ninth piece aside and takes, sorry, 10th piece aside, and takes 9 pieces and tries to train, test it on the 10th one. Again, no, 8th one, 9th one it takes, keeps aside, takes the rest of the 9, trains it, tests it on the 9th one, 8th one keeps it aside, like that, right? Ultimately, it takes an average of all those uh, cross validation, subset, the small pieces cross validation scores and the 9 pieces training scores. If it is balanced, then the model may work best on the train set also, right? Cross validation helps you determine whether model works well on the test set and production or not before you touch test set. Did you get it? Did you remember?
Yes, sir.
Right. So like that, right here, there is no need to do cross validation on the bagging classifier, because when you are doing bagging classifier, you are actually taking subset of data, right? There is one record which is pending, right? While building the first model, you have got fourth record which is there in the train set. You can use that record to test. That is useful as cross validation record. Here, third record, you can use that to test. You hear this is the here of third record. You can use that to test. So when you build individual decision trees, you can test them using individual, those remaining records. Okay. So that is like cross validation only. So if the model is working on those left out records, you can say the model will work best on the what you call it as test set and production also. So that is called as OOB score, out of bag score. Okay, out of bag error we call it as out of bag records. The records taken to build our bag of records we take and try to build the model. The records which were not taken and kept in the train set are called as out of bag errors, out of bag records. For each model, there will be a different out of bag model, and the algorithm will try to test the model using that remaining record, and how the models, individual models are working. Based on that, it will find out whether the model will work best on the test set or not. Got it? That is called as out of bag error. In interviews, right, they'll ask what is out of bag error, OOB score and out of bag error. To find out OOB score, there is a there is a parameter called as OOB score is equal to true. While fitting the model, it will actually calculate that OOB score, and in the algorithm there is OOB underscore score underscore which gives you out of bag error. So most probably on the test set and production also it will give 90% accuracy. Okay. So cross validation technique no need to use on the ensemble models, especially bagging and decision random forest algorithms. Got it?
Pasting also looks like the similar way, right? But is it not applicable?
Yeah, similar only. Only replacement will not happen. Sampling with replacement, sampling without replacement. That's it.
There also this kind of score is there or not? OOB is mentions like in the bagging. We can't hear you, sir.
I switched the network again.
Okay. So what I'm saying is bagging, it actually, as you said, it actually left one record which can be used for testing. So in the pasting also, we are actually taking randomly two each time, and the two are left over.
Yes, sir.
And it may be, based on if we mention 3 sample size equal to 3, it takes 3 and leaves 1. So the OOB score can be used there also?
I didn't listen to your question, sorry.
Yeah, it's okay.
Could you repeat?
OOB is specific to bagging, or it applies for pasting as well?
Algorithm is same, right? Bagging classifier only. If you say bootstrap is equal to true, it becomes bagging algorithm. If bootstrap is equal to false, it becomes pasting algorithm. That's it, right? Algorithm is same. So the OOB score also applies to both.
Okay. So the name actually says bagging, right? That's what whether it I was having a doubt of whether it applies to pasting or not.
No, yeah, same.
Sir, out of bag score, can you please explain that calculation of out of bag score?
Calculation in detail, I don't have a whatever that. So on the first model, you have left out fourth record, right?
Right.
On this model, it will predict and take the accuracy score and keep it. Right? On the second record, there is a third record missing. It will calculate score and keep it aside. On the fourth record, in the cross validation, how is it happening? On each of the subset, it is trying to build a model and take the other subset and trying to calculate the score, keep it aside. Here also the same thing. It takes average of all those left out records scores and keeps that aside. Got it?
Okay.
And it takes the actual model's scores and takes the average and puts it aside. OOB score you can see, and original score also you can see. Then if both are kind of close to each other, right, then model works well.
Okay, sir.
Okay. Okay, no, so that you got it right.
Yes, sir.
So out of bag evaluation, out of bag instances. When bagging, with bagging, the sampling technique is bootstrapping. No, the sampling is done with replacement. This means some instances are sampled many times, and some are not sampled, right? So it's a random sampling. So sometimes maybe the same record is sampled many times, and some are not. Suppose 60% of the data is sampled each predictor. Remaining 37 is called as out of bag samples. Using those, we'll actually try to do the cross validation. We can use out of bag samples as cross validation set. We can do this scikit-learn using OOB score. OOB score gives you the cross validation score. Okay. And anyway, you have model, you can actually predict and calculate the accuracy score also. You compare these two. If they are same, then the model will work on the test set also there. You can do cross validation also if you want. Okay, not a problem. But OOB score is already there. Okay, got it. See, I have got a question here. OOB score we said which metric it is taking, right? Accuracy score or F1 or there is no parameter for metric here.
Precision.
Huh? Sorry.
Recall precision.
Where is it mentioned?
No, you said 2 and I said 2.
Oh, okay. Sorry. I thought that you know the answer. Maybe we should look at the code, right? We can actually look into the code source here, right? In that we may have that. X comma Y, it is saying that we score, calculate out of bag prediction score. Right? There is a comment, no implementation. Abstract method. But default maybe it is
Maybe that is
using,
implemented in the child class. Maybe that whatever we just checked now is in the parent class maybe.
no, this is the class, no child class there, right? So maybe in the decision tree we have decision tree classifier, maybe the OOB score implementation is there. Let us see. We can look at that. No, I just now I got that doubt. So because we may take this model and try to do F1 score or precision or recall or accuracy score. By default, it may be looking at accuracy score only. OOB score is accuracy score only, but there is no mention of it. Most probably it is accuracy score. Okay, we'll see that. Maybe we have to dig through it a little bit. We'll know it. Okay, that's where I was saying, right? You can use the cross validation techniques also. If you are specific on some metric, for this model you need the precision high, recall high, then you should actually do the k-fold cross validation and take the metric you want to, and then assess whether model will work well on the train set and test set. Okay. and then random forest classifier.
1 second, sir. So this bagging classifier can also use the logistic regression, as you said, right?
Yeah.
So the sampling actually happens in the same way, but the algorithm will only change.
That's it. These algorithms will change. These will become logistic regression.
Yes. Okay.
Okay. So now random forest. Bagging classifier we have seen, right? The same way random forest also works. But random forest by default will not do sampling on the records. It will actually do sampling on the columns. It will not do sampling on the rows. Let us see. Let us see the class, you will understand.
I have
Right,
one more question, sir. Sorry for that.
Yeah, go ahead.
So we mentioned the number of features, right? So if we say number of features, let's say we have 100 features, and if we say somewhere 40 or 50, so it takes only those features for all the samples, only those 50, or we can
random 50 for each model. Random 50, random 50, random 50.
Columns also, right? Features.
No, you have to specify. You want column sampled, row sampled. See this?
Yeah, rows sampled. It takes randomly.
By
whatever.
default, rows sampled. Bagging classifier, by default, rows are sampled definitely.
Okay.
Bootstrapping is true.
Yes.
So it will sample, it will replace. But columns you want to say do it or not, you need to specify. Bootstrap features, false it is. If you say true, then it will actually take the features also. Right? N features, somewhere N estimators. Right? This is the features. Base estimator, N estimator, N estimators. Yeah, it's the features. Max samples is the rows.
Here, max features is also there.
Yeah, this
Below
max
that.
features is also there. Yeah.
So if we say the features, will it take only a column, but will it take only a set, or it takes randomly?
Random. Again, it is
randomly
random.
different features for each sampling.
Yeah, that's the point. That's the key.
Yes.
To avoid overfitting. I'll explain that in a moment. Why that different sampling will avoid, then you will understand, right? I have an example for that. In a moment, I'll explain.
Okay, sir. Okay, sir. Go ahead.
So that's the key. Basically, that's the key. And some interviews they'll ask who understood random forest, right? They'll ask why decision tree is not used. If you ask me, right, I'll not use decision tree in production, right, in real time. I'll use random forest bagging definitely because it actually solves all the problems which are there on the. It uses the power of decision tree and avoids the issues, the overfitting and other issues. So we'll see that in a moment. Random forest is an ensemble model of decision trees. Random forest uses only decision trees, no other algorithm. Random forest picks up a subset of features randomly and searches for best feature among the subset. Right? This is the right subset. Random forest picks subset of features randomly. Till that you take it. Searches for the best feature. We'll see it that in a moment. Okay. Randomly it picks features and then tries to build the model. With few exceptions, random forest classifier has all the hyperparameters of decision tree, right? Pulls all the hyperparameters from bagging classifier to control estimator. So you can use bagging classifier to reproduce random forest. Random forest is a specific bagging classifier. Okay? Bagging classifier is a generalized one. You can build any kind of estimator, any kind of ensemble model there. But random forest is specific to decision trees and with some kind of restrictions there. Okay. So if you look at random forest, n estimators 100. Right? N estimators is 100. So it is changed from 10 to 100. N estimators means features. By default, it will choose 100 features. If it is less than that, it will take all the features. Okay, criteria, we know that, right? Gini and entropy. This is for decision trees. Max depth, right? How much depth it should have. Each tree should have how much depth. If the depth of the tree is high, each model will overfit. In the ensemble model, each of those models will overfit. If the models are not overfitting, right, they are weak learners or underfitted models. If you take more weak learners, take average, then the model will work better. Okay, that's the basic idea there. Okay, and then max features, right? By default, it is square root. If you have 100 features in your data set, it will take square root of 100 as the number of features randomly picking, right? 10 features randomly it will pick. Okay. Bootstrap. Here also we have bootstrap. If you specify bootstrap, this is true, right? Bootstrap true. It actually takes the, rows also like a random forest. If you specify false, right, it's not going to take bootstrapping. So here, the random forest classifier and n estimates we are directly specifying because we know that the algorithm used is decision tree. Okay, I specified the other parameters here, but I should take out this -1. And then now fitted the model and did predict. I've got 91.2. Okay, so that is random forest classifier. Bagging classifier, random forest classifier works similar, but random forest classifier is specific to decision trees, and it does sampling on the columns definitely. And in the new version, right, they changed this also, right? The bootstrapping is not true in the old versions. They actually changed it to true here. Bootstrapping is false. If you kept false, right, the number of rows are not going to be bootstrapped. It will take all the rows, but specific columns if you specify it as false. Okay. So what is the advantage? We'll see that in a moment. Right? Feature importance we'll see, but let us look at these diagrams. Random forest will solve overfitting issue of decision tree. Okay, how? So I have taken a decision tree here. Let me magnify this. So there is a data set like x1, x2, and y. Right, x1 is a, x2 is a, then 1, b, b, 0, c, c, 0, c, a1, a, b1, right? Like some data set it is. Okay. If I have to build a tree, right, what I need to do, I need to make a split, right? If x1 is equal to a, on this column I am making the split. X1 is equal to a, then there is subset, there is subset. Again I am saying x2 is equal to c, there is a subset, there is a subset. X2 is equal to a, there is a subset, there is a subset. All the leaf nodes are pure. Right, now this is the decision tree. I need to make prediction on c and b. Right, x1 is equal to c. Can I move? The first, tree first node, the condition is based on x1 is equal to c. Can I move anywhere? Will the model be able to predict? Will the model be able to predict?
It will take the right branch, right? It will take the right hand side. It will take the right hand side.
Yeah,
branch.
right hand side. If you have x is not equal to a, then no c, right? So you come not b or not c. It may be b, it may be c, right? I came to right side. Yeah, now x2 is equal to x2 is equal to b, right? x2 is equal to b. Again, it can actually come to this side. It may predict, but it may be overfitted, right? It may be overfitted in the sense the prediction may be right, may be wrong, because there are two possibilities for x2. If it is not a, there are two possibilities, b and c, right? Got it? Got it? If the combination CB is not present in the data set, we may predict, but it may be right, it may be wrong. We are not sure. Okay. So in this situation, right? So if you try to build an ensemble model, it will actually solve the problem. The probability of making right prediction will increase because there will be multiple models. Okay, see that here. So I have taken the same BC prediction, right? So I built with x1 one model I built, with only x2 another model I built. This is ensemble, right? I have taken the data and then sampled on the columns. This is random forest algorithm. Random forest algorithm actually samples on the columns, right? So out of 2 columns, I have taken 1 column and built 1 model. 1 column, I built 1 model. If you have 10 columns, you may actually do, if you want to do 2 columns models, right? Maybe x1, x2, you build 1 model, x1, x4, 1 model, x1, x5, 1 model, like that, x1, x3, x7, 1 model, like that you will do. Randomly I chose and I built a model. Now, if x1 is equal to a, there is something, right? X1 is equal to b, there is something, right? And then if you are not building a complete tree, that there is another question I should have answered. Here, I am building a complete tree where at the end, the leaf nodes are belonging to one particular record, okay? But in this particular case, see this, all the records are not belonging to one class. All the records are not belonging to one class. All the records not belonging to one class, right? So in this case, right, the model will actually try to make predictions using the probability, right? If you know, if x1 is equal to a, right, it comes here, and the data set is not right. That's where it is actually coming like that. You know, it's a synthetic data, right? Once it comes here, 2 A's are belonging to 1 and 1 A belongs to 0. Most probably A belongs to 1. That's how it makes prediction. The model prediction is going to be 1. So here, if it comes this side, right, B probability is 1 by 2 and C probability is 2 by 3. So it's going to predict C. Like that it's going to do. If tree is not built completely, it depends on probability again. Got it? Got it? If tree is not built completely, leaf nodes are not going to be pure. Do you agree with that statement?
Yes.
When leaf nodes are not pure, it actually depends on probability to make predictions. So now the record is what? B and C, right? C and B. So x1 is equal to C. So x1 is equal to A, no, it will come this side, right? X1 is equal to B, no, it will come this side. C probability is going to be 2 by 3. Right here, C probability is going to be to become 1 is going to be 2 by 3. On this side, x2 is equal to B. So it will come this side, and x2 is equal to B, it will come this side. It's going to be 1 by 2. When you take average of these two probabilities, it's going to be 0.45, 58. We predict 1 as CB. But if you take this, this normal decision tree, the probability, the outcome came as 0. But when you did the prediction using the ensemble model, the random forest model, we got 1, right? There is difference, right? Most probably this is going to be better when you have more columns and you are building more number of subtrees. The probability of becoming this prediction correct is going to increase. Got it? Got it? That's how the overfitting problem is being solved. What is overfitting? Model works 100% on the train set. When you take the other records, right, it may not predict well. That is the overfitting, right? That problem we are trying to solve here. On the train set, it works decently. On the test set and production also, it works decently. Got it? Yes, no?
Yes, sir. But this probability applies to the original decision trees as well, right? If we are cutting off the max depth. So if we are not allowing the tree to become completely pure.
Yes. Okay. Because if it is not pure, there is a dilemma, right? If it's not pure. If you look at our decision tree algorithm, let me show you that. Decision tree, this thing. We built a decision tree, right? So here, if I chop this, if I say the max depth is equal to 1, 2, 3, right? It will come there and stop. See this here, there is uncertainty, right? So the model may take the probability to predict. Okay.
So again, there exists a concept of threshold and all the stuff over here.
Threshold, it is after building the model, threshold comes into play.
Okay.
Right? By default, random forest also takes 0.5 as the threshold, 0.5 as the threshold.
Yes.
And if you want, right, we can take control of it, by looking at the probabilities and all.
Yes.
Okay. So that is on the random forest and how it exactly, fixes the overfitting issue of the decision trees. Decision trees are powerful, but the overfitting is the problem. So we are actually trying to solve that. And other thing is, even if you add multiple records or remove records, right, the decision of these random forests will not change much. The structure of the model will not change much because we are taking subsets, right? Sometimes some records, some subsets may get affected, some subsets may not get affected. That way, the model is going to stay a little more stable when compared to decision tree. Got it? It's all logical. You need to think. Got it, right?
Sir, here we have taken the example of only features, right?
Not Sam, not rows.
Rows. So if we take rows, so every diagram here becomes the multiple trees.
Yeah, multiple trees, and that's where we are taking 500 trees, 300 trees like that. Right? If you take n estimators, it's 500. Right? So all combinations it will try to cover. Right? It is like it is like trying to take data combinations only. When you actually take subsamples, they're all like you started 1 year ago, you will have only 10 records. You started 6 months ago, you'll have maybe 10, maybe 200 records. You started now, you may have 1,000 records. Like that it is, right? You are trying to look at different combinations and then trying to make the model understand. Got it?
Yes.
So feature importance is another good thing that is used extensively. Okay, when we looked into the p-value based feature importance, the algorithm is not satisfying the assumptions of the data. The data is not satisfying the assumptions of the algorithm. You cannot take p-value seriously. The feature selection is not correct. But when you do mathematical approach, the regularization, there is no dependency on the assumptions. The scores assigned to each feature may give you the importance of the feature. In random forest also, you have an attribute called as feature underscore importance underscore. Even decision tree also has got it, right? In decision tree, the feature underscore importance underscore is the Gini score, Gini gain, or the information gain score. Okay. In random forest, the feature underscore importance underscore is more accurate compared to decision tree, because if one feature is becoming the root node of many trees, what that means, right? You built a random forest algorithm with 100 trees, right? On all the 100 trees, most of them, maybe 70% of the trees, one feature became the root node. That means what? X5 became root node. That means what? Is that the most important one or most unimportant one?
Most important one, because it is classifying.
It is distinguishing the data very clearly in any combination. When there is any other feature is present, right? It is distinguishing. That's how the score is calculated. This score is more accurate when compared to individual decision tree because it is calculated based on many models, right? You can actually sort it by descending order. So you know in that digit recognizer data set, this pixel is more important. Right? This pixel is a little less like that. Okay. So I have taken only the feature importance is more than 0.001, maybe around 400 features I would have that. So these features are most important. Okay, if you take only those features and try to build a model, then also model works the same way as the original one. Okay, 0.96 I think I took. No, I did not. I just showed the feature importance here. You can actually produce a, in NLP problems, there will be a question. Can you identify the best words that are actually making the model understand whether it is a good sentence or bad sentence? Sentiment analysis we call it as. Right? You got a sentence or you got thousands of sentences, and there are flags, zeros and ones on the data, and you built a model, and client will ask you, can you tell me which words are most impacting in making the decision whether it is good or bad. Then you can take the feature importances of each word and then do a graph which actually shows you that the feature which is important. We have done it. One thing I'll actually show you in a moment. Let me start.